Hello, everybody. So we are going to continue the introduction that we started last time about the reactions and the heats of reaction, and there are some notes that we need to know, which are important notes actually. The first is already something we mentioned before, that the heat of reaction is going to be negative if the reaction is exothermic and positive if the reaction is endothermic. The second is that heat of reaction is a function of both temperature and pressure. So if there is any change in pressure or temperature or both, then the heat of reaction will be different. However, in this chapter, we are going to deal with cases where the pressure is low and moderate, which is close to low. And in these cases, the effect of pressure is not very high on the heat of reaction. That's why we will assume that the heat of reaction is only a function of temperature, not pressure. So this is valid for as I said, the cases of low pressures. But if there is big change in pressure, or the pressure or the reaction is taking place at very high pressures, then the heat of reaction must be calculated according to or taking pressure into consideration. There is one more point here, which is that the value of heat of reaction, which is the number that we write after the reaction here, is dependent on the stoichiometry of the reaction. Meaning that we said last time that when we have a reaction like this, with this heat of reaction, it means that this heat is produced when 1 mole of methane reacts with 2 moles of oxygen, producing 1 mole of carbon monoxide and 2 moles of water. So these numbers, it's not the ratios, the numbers, the number of moles, 1 mole and 2 moles, 1 mole and 2 moles, this is what produces this amount of heat. So if I rewrite the equation with the same ratios but with different coefficients, as we see here in this case, we have this equation is the same, but the second is the first multiplied by 10. So this means that the heat of reaction will also be multiplied by 10. And again, recall the mathematical definition of the heat of reaction. So the value is going to be the same. So negative 190.3 over 1 mole of methane is the same as negative 8903 divided by 10. So it's the same value. So it doesn't matter, as long as we multiply the equation by the same factor we multiply the heat of reaction with, then the equation is the same. And again, this is something that we need to understand, that what we do is description of what happens in reality. So we shouldn't expect that the heat of reaction would be different, or the amount of heat the reaction is producing would be different just because we wrote the equation in a different way. So we describe what happens in reality. What happens in reality is what happens. It doesn't depend on how we describe it. So when we describe it in different ways, the result should be the same, as long as we are describing it the correct way. The next point is that the value of heat of reaction also depends on the phases. For example, if we have the same reaction that we just mentioned in the previous point, for the combustion of methane producing carbon dioxide and water vapor, we can write the and you notice that we write the phases. So we have here 1 mole of methane gas reacts with 2 moles of oxygen gas, producing 1 mole of carbon dioxide gas and 2 moles of liquid water. So if this is liquid, then this is the heat of reaction. We can rewrite the same equation with vapor phase, not liquid phase. And if water is vapor, then the heat of reaction is going to be different. And the difference is very expected, that the difference is going to be the latent heat of vaporization. And this is what you would notice, or you'd find out if you pick the value of heat of vaporization of water at 25 degrees Celsius. We already have all the values of heats of vaporization of water from the steam tables. So if you go to the steam table, you'll find that the latent heat of vaporization of water at 25 degrees Celsius is 2442.5 kilojoules per kilogram, with some unit convergence to convert this from kilogram to kilomole, and then from kilomole to mole. Then we will have the value, of course, multiplied by 2 because it's 2 moles. There's going to be almost 88, which is the difference between these two values. So this is what happens if you write the equation with different phase, then the difference is going to be the latent heat. One last point here is that we have in the rest of this chapter we will be dealing with mostly with what we call the standard heat of reaction, and we give it a symbol of delta H node of R. This node represents the heat of reaction at standard conditions. Standard conditions are 25 degrees Celsius and 1 atmosphere. So if we have the reaction taking place at these conditions, meaning that the reactants and the products are at the same temperature and pressure, this is what we call the standard heat of reaction. We will understand in one or two two videos, I think, or I think one or two videos, why we call it the standard heat of reaction, or why it's important, or why it's special conditions that we consider this heat of reaction at these conditions. Okay, so let's try to apply these notes on the few examples that we will see here. So first we have the standard heat of combustion of N-butane. Vapor is this is the combustion of N-butane. Of course, we need to make sure that the equation is balanced. I mean the stoichiometric coefficients are correct. So this equation is perfectly balanced, and we can check it yourself. The heat of reaction is negative 2878 kilojoules, and we want to calculate delta H dot, which is the rate of heat or enthalpy change in kilojoules per second or kilowatts if we have 2400 moles per second of carbon dioxide produced in this reaction, and the reactants and products are all at 25 degrees Celsius. So if we have the reactants and products are at 25, so they are the standard temperature. And we have the flow rate. So this is going to be a very straightforward case where we will apply the equation that we ended up with last time. So we said that the total heat or total enthalpy change is the heat of reaction multiplied by the extent of reaction. So we need to know what is the extent of reaction. We have here an information of 2400 moles per second. This is the amount of carbon dioxide produced, or the rate of carbon dioxide production, which is the difference between the feed and the product, or the product minus the feed, because it's a product in this case. So this is the NIR, which we call the NIR, or N carbon dioxide R, which is 2400, and the stoichiometric coefficient is 4. So in this case we have the extent of reaction can be calculated to be 2400 over 4, so this is 600. And then we will just substitute in the equation. We multiply 600 by this number to get the total enthalpy change due to this reaction. So it's very straightforward thing. For the remember the numbers here, because we are going to use the same numbers for the same equation, but with one small difference. Here we have the same equation with the same heat of reaction, with the same phases, with everything is the same, and we want to calculate the standard heat of this reaction. So let's do this first, and then we will see the next point. So if you check this equation and this equation, the difference is that we multiplied this equation by 2. So this is the result of multiplying this equation by 2. So the heat of reaction will also be multiplied by 2. So this is the heat of reaction. Or from the definition of heat of reaction, we say that the amount of heat produced per 4 moles of carbon dioxide, for example. So this is divided by 4 equals this number divided by 8. So this number is going to be double the heat of the first reaction. So this is the first point. The second point is that if we want to use the second equation to calculate delta H for the same molar flow rate. So it's the same number as before, but we will applying this flow rate on the second equation, not the first. So what we will do now is we will calculate the extent of reaction. The extent of reaction, as we said, is the number of moles that reacted, or the rate of reaction, or the rate of molar rate of carbon dioxide produced, divided by the stoichiometric coefficient. Now the stoichiometric coefficient of carbon dioxide is 8, so it's going to be 2400 divided by 8, which is 300. So when we calculate the total heat that is or the total enthalpy change, is going to be 300 multiplied by the new heat of reaction, which is going to be the same. So if you compare these numbers to the numbers in the previous example, we divided the extent of reaction by 2 and multiply the heat of reaction by 2. So it's the same thing. So it doesn't matter. And this is what I was telling you before, that it doesn't matter how you describe the natural phenomena, which is the enthalpy change. The phenomena doesn't depend on the way you describe it. So it doesn't matter how you write the equation, the result is going to be the same at the end. One more example here, and this is an interesting one. So here we have the same equation, the same reaction, and we want to calculate the heat of reaction of the second reaction given the heat of the first reaction. And if you compare these two reactions, they have the same coefficient. So I didn't multiply by factor like the previous example, but we have different phases. You would notice here that the butane is gas and here it's liquid, water is liquid and here it is vapor. And we said before that the difference is going to be the latent heats of vaporization of butane and of water vapor, or of water. But the question is, shall we add the heat of reaction to the latent heat or subtract the latent heat from the heat of reaction? This is the question. So to answer this question, we need to go in a systematic way. We understand, or we know that this heat of reaction, as we discussed last time, that this heat of reaction is the difference between the enthalpy of the product and the enthalpy of the reactant. So it's the enthalpy of these two minus the enthalpy of these two. So I can write this heat of reaction as 5 times the enthalpy of liquid water plus 4 times the enthalpy of carbon dioxide, or the specific, of course, the specific enthalpy, minus 1 multiplied by the specific enthalpy of butane minus 13/2 multiplied by the specific enthalpy of water. Here butane is gas, here liquid water is liquid. For the second reaction, we can do the same. We can describe the heat of reaction as the same thing. The only difference between these two equations is in the phases of butane and of water. So we understand and we know that the vapor, the enthalpy of vapor, if it's saturated liquid, then it is going to be the enthalpy of the liquid plus the latent heat of vaporization. So to turn the liquid into vapor, we add the latent heat of vaporization. So we can write this term as the enthalpy of liquid water, which is this term, the enthalpy of liquid water plus the latent heat of vaporization. And the same here, for the liquid, it is the gas minus the latent heat of vaporization. So this is what we do here, and we can rearrange the equation to be written so that we can group this number with this, or this term with this term and this term, and these three terms, which are this and this, are of course, and water. These are the same terms we have here. So this is going to be the latent heat, or the heat of first reaction, the standard heat of the first reaction, plus 5 times the latent heat of vaporization of water, minus negative the latent heat of vaporization of pentane. So it's going to be plus this and plus this. So this is one way of doing this calculation. There is another way, which is I prefer the second method because it's going to be something we will use later, which is something we said many times before, of creating a hypothetical path. So if you want, we can say that we have butane plus oxygen go to carbon dioxide and liquid water. Here butane is gas, and we know the delta H here. And we have butane liquid plus oxygen to produce carbon dioxide and water vapor, but we don't know this latent heat of vaporization. This is not known. So one thing that we can do, which is a very, for me, this is easily understood step, is to create a hypothetical path. So we can change the conditions of the feed from the conditions of the reaction that we don't know its heat of reaction to the conditions of the reaction that we understand. So we can add the latent heat of vaporization of butane because it's liquid. So to turn liquid into gas, we have to add the latent heat. So this is one step. The second step is to perform the reaction with the known conditions, and then to change the conditions of the product to be the conditions of the product in the second reaction. So the difference between this and this is that this is liquid and turning into vapor, so we add latent heat. So this is, of course, this is 5 times, but I'm just talking about the general term, or the general idea. So we add here to go to the conditions of the known, or the feed conditions of the known reaction, and then we add latent heat to go from the product conditions of the known reaction to the product conditions of the known reaction. And this is how we can do this. And now we can get the heat of reaction. So it's the same equation as before, but for me this is easier to understand, and this is personally for me. For you, you might, you feel that the first method was easy. Anyways, whatever method you like, it's fine as long as you do this correctly. For the coming videos, we will start with some interesting methods that are important actually, and they are the methods that we use to calculate the heat of reaction. So for the examples that we solved in this video, we were talking about calculating the heat of reaction with the knowledge of another heat of reaction. Whether we change the phase, we change the coefficients, or multiply by a factor, whatever the change that we make, it's just change in the same reaction. But now we want to see if we want to calculate the heat of reaction with the knowledge of, or without knowing the heat of the same reaction at different conditions. We have three methods: Hess law, using the heat of formation, and the heat of combustion. So these are going to be the topics of the next videos, inshallah. So I'll see you then. Goodbye.